So as I mentioned last time, this random field Ising model, according to the arguments by Parisi and Sourlas, at the critical point it should have supersymmetry, and then there's a mystery why the supersymmetry is not always there. But first, let us today I'm planning to give the original argument for the presence of supersymmetry. So it's good to know the basic arguments before we study the caveats. And also I will explain why supersymmetry implies dimensional reduction. So this is going to be the plan for today. So we are going to be interested for the rest of these lectures at the critical point of the random field Ising model. And at the critical point, as usual, we are allowed to use, instead of the lattice description, we are allowed to use effective field theoretic description. So we are going to study the action, which is going to depend on a scalar field phi. So it's grad phi squared. Then there's going to be a potential, and there's going to be coupling to a magnetic field. So that's going to be our action. So the potential is the quartic potential, squared phi squared plus lambda phi to the fourth. And this magnetic field is a random magnetic field, so it's a quench disorder. So we are going to assume that it's a short-range correlated quench disordered magnetic field. So the average value of hx prime is equal to some constant delta times delta function of x minus x prime. So this delta plays the role of the constant that I denoted last time by kappa squared. So today I'm going to denote it by delta. And so in this model, we are going to do perturbative expansion. So we can expand correlation functions of phi. In perturbation theory, there's going to be perturbation theory in the quartic coupling lambda and in the magnetic field H, which we then average over. So this perturbative expansion is very standard. So let me remind you how this works first for the situation without magnetic field. So this would be the pure Ising model. So if you do pure Ising, so we set H equal to 0. Well, in that case, when you compute correlation functions, so we just do Feynman diagrams. So for example, suppose you study phi correlation function, then okay, there's going to be a propagator, then there's going to be some correction at order lambda squared. Okay, for the 4-point point correlation function, let's say connected correlation function, there are going to be diagrams like that, plus some correction again at order lambda squared. So this is all very standard. So now let us see what is going to change in the presence of the magnetic field. So now suppose that we now have this magnetic field H non-zero. So what's going to change for this perturbative expansion? Well, the first thing which is going to change is that we are going to have this new coupling H phi. So there's going to be a new vertex. So in the theory, in the pure Ising, we just had quartic coupling, which was the only vertex. Okay, there was also the propagator 1 over p squared plus m squared in momentum space. So now we turn on a non-zero H, but let us just keep it fixed for the moment. It's non-zero but fixed. We don't yet average over it. So in this case, we have a new vertex, and I'm going to denote this vertex like this. So there's going to be H sitting at some point x, and okay, it couples to the field phi. So this diagram, this is going to be a notation for this new vertex H phi. So I can write this in position space, or I can write it in momentum space. So in momentum space, this h phi is integral of hp phi minus p over all p. So I can work in momentum space, I can work in position space, depending on how it's more convenient. And so now I have to do a perturbation theory in presence of this new vertex. And in the language of quantum field theory, this sort of new vertex is usually called tadpole. And the main consequence of this vertex is that the expectation value of phi in the presence of this field H is going to be non-zero, is going to become non-zero. So let's see why it is non-zero. So this phi, average value of phi in presence of H is going to be computed in perturbation theory as a sum of Feynman diagrams. So this is going to be this diagram. This is zeroth order diagram. Then there's going to be a diagram like this. So here there is a quartic coupling lambda, and I'm using 3 magnetic fields H. Then there are going to be corrections to this formula. For example, there's going to be a correction like this. You know, I can use 2 quartic couplings, lambda lambda H, and then here I can use 3 more HH. So I can do something like that, and there are going to be many more diagrams. So just to understand, just to make sure that we understand what's going on, let me just write in an explicit form the value of, for example, a couple of diagrams. So what does this diagram mean? So this diagram, let's suppose that this point is x. This diagram gives a correction to the one-point function phi of x, which is equal to the integral over dy, the propagator in the position space g of x minus y, times the magnetic field at the point y. And so this g is just the Fourier transform of 1 over p squared minus plus m squared. So this is the value of this diagram. And if for example, if I want to compute this diagram, then I would have to introduce a propagator g for each one of these legs. And there would be a point here, say y, and 3 points z1, z2, z3. And this is still point x. And then I would have to write an integral where I would have to integrate over y, integrate over z1, z2, z3, put a magnetic field at z1, at z2, at z3, and also all these propagators, g. So that would be the value of this diagram. So I have this perturbation theory. Here I wrote it in position space, but of course I can do it in momentum space as well. Okay, so let us keep this in mind. But I can also write similar diagrams for higher point correlation functions. For example, I can write the correlation function phi in magnetic field H. So here I wrote it without magnetic field H. Now I write it in magnetic field. So what's going to be the answer? Well, I'm going to get the same answer as in the zero magnetic field. So they're going to be this sort of diagrams. Plus, I'm going to get some extra diagrams. So because of this vertex, because of this new vertex. So for example, I'm going to get this diagram. So let us suppose that this is phi of x, phi of y. So I'm going to get, for example, this diagram, x with the magnetic field and y with the magnetic field. That's going to be one diagram that I'm going to get. But which other diagram I want to show? well, for example, this diagram is going to be also present. So x, y, lambda, and then two magnetic fields, H, H. So there are many various diagrams. So that's OK. So that's the end of the first step. So the first step, I take a correlation function that I'm interested in, and I write a perturbative expression, including this new vertex. Now I'm going to the second step. The second step is that I have to average. Let me write it here. So second step is that I have to average over h. So I have to use the propagator, which I wrote there, h of x prime is proportional to the delta function. And so what does this mean? It means that this basically amounts to saying that there is a new propagator which connects these crosses. And this propagator is this delta function. So it's delta times the delta function in position space, or in momentum space, it's delta times p to the 0. Right? And so using this propagator, I'm supposed to average these expressions that I got. And what does it mean to average? Well, it's Wick's theorem. It means that I have to consider all possible contractions of crosses using this propagator. And so that's going to be now an averaged value of my correlation function. And so let us consider some examples that we are going to get. So for example, if we take the average value of phi in the magnetic field H, and now we average over H, what are we going to get? We are going to get 0. OK, this is obvious by symmetry that we are supposed to get 0. But this is also obvious from this formal expression in terms of diagrams, because I have an odd number of crosses, and I'm supposed to join crosses pairwise, and I cannot do it here. So I'm going to get 0. On the other hand, if I take, for example, if I take phi h, if I take a 2-point function and I average it, well, then I'm going to get something non-trivial. So let me first consider the case, what I'm going to get at lambda equals 0. So if lambda is equal to 0, then I have this diagram, which is just the propagator. And then I get this diagram. Well, I take two vertices and I join them by this propagator by the dashed line. So what does this give me? So the first diagram is 1 over p squared plus m squared in momentum space. And this is, well, delta from here. So this is delta divided by p squared plus m squared squared. And that's it. So that's, if lambda is equal to 0, then this is the full answer for the averaged 2-point function of phi. OK, so that's this. I want to make here the following observation. So yesterday there were some questions by some members of the audience. People wanted to get a better intuition of why a quenched disorder magnetic field is different from just having an extra field in the Lagrangian. So this allows us to see the difference. So suppose that instead of treating H as quenched disorder, what I'm doing here, I would integrate it out. So suppose that I wanted to integrate out this H. So the action for H is e to the minus h squared over 2 delta. This is the measure of integration for H. Suppose that I integrate out H. So H couples quadratically to phi, linearly to phi. So if I integrate it out, then this would give me a new term in the action, which would be just a correction to the mass of the phi field. So this would be a new term that I would have to add to the action, because I would be doing a Gaussian integral, h integrated out, so I'm going to get a new term for phi with a minus sign. So if I were to do this, then the propagator for phi would become 1 over p squared plus m squared minus delta. If I were to take this propagator and if I were to expand it in delta, then the linear term would be exactly the same as what I have here. So it would be 1 over p squared plus m squared plus delta over p squared plus m squared squared, but then plus all the other terms. Now you see that if I treat h as a fluctuating field in my action, then I get this propagator. If I treat h as a disorder field, then the expansion truncates at the first term in delta. So I clearly get a different answer depending whether h is a disorder field or a fluctuating field in my action. And so if I treat h as just a disordered field, as a fluctuating field, well, I get a really boring answer because it just amounts to the shift of the mass. So clearly, by shifting the mass, I cannot change the universality class of my phase transition. While here, in this expression, things get very interesting, because if I now take the limit when m squared goes to 0, then this becomes 1 over p squared plus delta over p to the 4th. So I get a very different scaling of the propagator at small p. And so this is going to be the reason why the universality class is going to change. Okay, so just to make sure, this is, I'm not supposed to do this. This is the right thing, and this would correspond to a completely different physical situation. So, okay, so here I considered the case lambda equals 0, but now going back here, I can also consider lambda not equal to 0. Well, then I get a bunch of additional diagrams. For example, I get this diagram. I get this diagram with 2 crosses. It's this diagram here. And then I would have to connect this by the dashed line. And you can consider many more diagrams. So that was for the correlation function phi h average. Interestingly, since we are in a disordered theory, we can also consider different sort of correlation function. It's also interesting to consider a correlation function where I take phi, average value of phi, at the point h times the expectation value of phi at the point y in the same magnetic field h, and now I average the product. So it's interesting also to consider this quantity. Why is it interesting? Because we might wish to consider something which is called the susceptibility. The susceptibility is the derivative of the 1-point correlation function phi of x in the point at the magnetic field h, which I differentiate with respect to external field, which I call here h, which I add at the point 0. So I take I take the 1-point function of phi, and now on top of the average, on top of the random magnetic field small h, I add an additional deterministic magnetic field big H, and I add it at the point 0, and I see how my 1-point function changes. So this is the susceptibility. And this susceptibility, you can show, okay, this is an exercise. You can show that this susceptibility is equal to the difference of two objects. This susceptibility is equal to the difference of phi of x, phi of 0, in the zero magnetic field minus this new object that I consider here. So phi of x, phi of 0, h, everything is averaged. So since susceptibility is an interesting quantity, well, this is an exercise, but just to give you an idea where the second term comes from. Okay, so you see phi here appears in the action. So it's kind of obvious that when you take this derivative d to the h, then the first term appears. That's kind of obvious. And the second term appears because also the partition function. So when we define the correlation functions, we divide by the partition function. And the partition function also varies as a function of big H. And so since we have to take this into account, you get the second term.
And you put capital H to 0 at the end.
Yes, thank you. So this susceptibility, if you take this and set big H to 0, then you get this difference. Thanks, Marco. Okay, so this is just a physical motivation, but to consider this product of two 1-point functions averaged, and for this object, when we do the perturbation theory, you don't get the first term. So you get only the leading term for this object is this. Plus corrections. And so this is this is delta divided by p squared plus m squared squared. So now what do we see? We see that if we focus on this average product of 1-point functions, then we just get 1 over p to the 4th term, while here we get the sum of 1 over p squared plus 1 over p to the 4th. Now let us go to the position space. So in the position space, we can so we are going to call the disconnected correlation function this one, phi of x, phi of y, h average. And because we have this behavior 1 over p to the 4th, it means that in position space, this disconnected correlation function goes as 1 over distance to the power d minus 4 at the critical point. So the critical point means m going to 0. Or rather, it would go like this in a Gaussian theory if we just set the quartic coupling to 0. But in a non-Gaussian theory, this would be corrected by an exponent eta or eta bar. I always forget. This is called eta bar exponent. You see 1 over p to the 4th, we go to the position space, we get d minus 4. On the other hand, if we consider connected correlation function, so the connected correlation function would be this difference. So it's phi averaged minus phi averaged. Then when we consider this difference, the 1 over pi to the 4th term cancels, and you're only left with 1 over p squared. So this means that this connected correlation function decays more rapidly at infinity. So it goes as r to the d minus 2 in a Gaussian theory. And in a non-Gaussian theory, there's going to be a critical exponent eta. And at the moment, this eta and eta bar are independent critical exponents. But we will see that supersymmetry is going to require that they should be equal. OK, so I explained how perturbation theory works. Now the next step is to understand a little bit more the structure of supersymmetry and to understand the value of the upper critical dimension. So it's going to be about upper critical dimension. And let us do this again by analogy with the pure Ising case. So in the pure Ising case, one can argue as follows. You do perturbation theory first at tree level. You compute some correlation functions. Well, everything is going to depend on the quartic coupling lambda. Then you start doing loop corrections. Well, you're doing perturbation theory. Well, when you do loop corrections, you are going to encounter diagrams, for example, at one loop of this form. These diagrams, they can appear, everywhere inside your Feynman diagram that you're going to consider. So let us study this Feynman diagram as a function of external momentum. So there's going to be some external momentum here, P. Let me assume that all of these external momenta are comparable to each other. And they're going to be momentum in the loop, which let me call it K. And so this momentum in the loop can be very, very large. So since I have here, so I'm considering the pure Ising case, pure Ising. So then the propagator here is 1 over k squared. So I'm going to have a loop integral, and this loop integral is ddk 1 over k squared, 1 over k squared, neglecting the external momentum for the moment. So this integral, I would like to study what happens with this integral in the limit when k goes to 0. Well, here I see, what do I see? That if d is larger than 4, then this integral is convergent as k goes to 0. So it's infrared finite. It's an infrared finite integral. On the other hand, if d is smaller than 4, then this integral is going to diverge at small k. Well, it diverges because now I neglected the external momenta. If I'm now going to put back the external momenta, they're going to cut off this divergence, and they're going to make this integral I. Let me call it I. It's going to behave at small momenta schematically as p to the power minus epsilon, where epsilon is d minus 4, is 4 minus d. So, so how do I interpret this? In this very pedestrian way, I just discovered that the upper critical dimension of this model is equal to 4. So if I'm at dimension less than 4, larger than 4, then perturbation theory is reliable. All these loop corrections, they basically don't do anything for me. All these integrals, they're going to converge, and they're just going to give some constant contribution to the correlation functions. No big deal. On the other hand, if d is less than 4, then these integrals are very, very important. So I discovered that the loop corrections are very important. Actually, they blow up at small p. So what I discovered is that perturbation theory is not reliable. It's d less than 4. And how do I interpret this? Well, I just say that what this means is that for example, my propagator, which was 1 over p squared in a Gaussian theory, in a non-Gaussian theory, it should be changed to something like 1 over p squared minus gamma. So there's going to be some negative correction. It has to be negative because in position space, the behavior is going to be faster at large distances. And so I can write some interpolating function like which interpolates between these two behaviors. I can write as 1 over p squared 1 plus p to the minus gamma. So this would be some sort of interpolating behavior between 1 over p squared at large momenta and 1 over p squared minus gamma at small momenta. And so what is happening here is that I have this behavior p to the minus gamma, and you see if I were to expand this term, okay, this term is very large, but if I were to naively to expand in this p minus gamma, I would get a series like 1 over p squared plus 1 over p squared times p to the minus gamma plus dot dot dot. So this would be a perturbative expansion, and here I see that every term in the perturbative expansion actually blows up at small p. So what we observed here with the perturbative corrections blowing up at small p is just a manifestation of the same phenomenon. Okay, so this was for the pure Ising. Let us now repeat exactly the same philosophy for the random field Ising. Let me take some quantity, some observable quantity. For example, the quantity that I would like to study is phi h, for which I already wrote this expression. 1 cross plus 3 crosses plus this diagram that I already wrote. But now let me write another diagram, which is going to be the important one. So let me do it like this. We keep 5 magnetic fields. So that's going to be the important diagram. So now this is before the average in H. I'm going to be computing some correlation functions. Maybe they're going to involve products of several quantities like phi h, and then everything else is going to be averaged over h at the end. So when I'm going to be computing this sort of quantities, the term that I would like to look at is a term where I'm going to connect these two crosses. So I'm going to get this diagram. Let me write it separately. So it's going to be a cross. Here I'm going to get this, 2 crosses, this. And now let me compare this diagram and this diagram with the leading diagram, with the leading or in lambda diagram here. So let me call this diagram 1, and this is going to be 2a and 2b. So the first observation is that the diagrams 2a and 2b, they have very similar structure to the diagram 1. So what you can say is that they renormalize the diagram 1. So there is a certain loop integral, and the number of external vertices is exactly the same. So just like I studied the problem here, I would like to understand in which dimension this renormalization effect becomes important. So in which dimension this renormalization effect becomes singular in the infrared at small external momenta. Well, for the diagram 2a, I know when it's going to happen. This diagram 2a, this loop integral, is exactly the same integral that I analyzed here. So this is going to become important. So it's going to become infrared singular in d less than 4. But what about this diagram? So this diagram is quite similar, except that I'm going to have an integral dk 1 over k to the 4th times 1 over k squared. Well, actually not 1, like delta over k to the 4th, because here I have delta. So this propagator becomes 1 over k to the 4th, and this is 1 over k squared. So this diagram becomes infrared singular much earlier. Becomes singular in d less than 6. And since this diagram is going to appear as you do perturbation theory in higher and higher order, this diagram is always going to keep appearing. So we have to conclude that actually the upper critical dimension of this model shifts from d equal 4 to a higher value of d. So the upper critical dimension is equal to 6. So that's the argument for the value of the upper critical dimension. Okay, but we can now say more than that. We can now use this argument to make a statement about the structure of perturbation theory in general, which is known as the dominance of tree-level diagrams in this theory. So what do I mean by that? Suppose that you compute any quantity. So I compute any quantity. Well, any. Let me take some quantity characterized by external momentum p external. And I compute the correction to this quantity in perturbation theory in order lambda, so in order lambda to the n. And I would like to study the leading effect, what is the structure of the leading correction to this quantity. So the leading relative correction at order lambda to the n is actually going to have this form. It's going to have the form lambda times delta to the n times p external to the power minus n epsilon. So they're going to be n loops. So each here epsilon is equal to 6 minus d, sorry. So one loop brings p to the minus epsilon. Here I explained p to the minus epsilon. now n loops are going to give me p to the minus n epsilon. I have to, in order to get this factor p to the minus n epsilon, I have to use for every lambda, I have to use 1 delta, because I had to raise the propagator here from 1 over k squared to 1 over k to the 4th using delta. So that's going to be the leading thing. And of course, there are going to be corrections. There are going to be terms here where I did not use as many deltas as I should have. For example, there are going to be terms like this, where I did not use any deltas. But all those terms are going to be suppressed with respect to this leading term. They're going to be suppressed by p to the delta squared. No, sorry, p squared over delta. P squared over delta. So that's the claim. Well, the claim that I basically explained, because if you want to get the most singular behavior, you have to use as many deltas as possible. As many deltas as you have lambdas. That's going to be the most singular behavior. And now I'm going to make the following trick, which is not totally legal. I'm going to say, okay, well, I'm interested in, so we are interested in the limit, in the infrared limit. So p external is going to go to 0. And I know that this, I cannot just drop these corrections which are singular in this limit, p external to the power minus epsilon. I have to resum these corrections, and the job to resum these corrections is, it's a job of renormalization group theory. It's clearly hard to resum them. And we are going to talk about this later. But what about these terms, these correction terms, like p squared over delta? So I just want to say that I'm going to drop these terms, because they are subleading to the leading terms that I want to resum. I'm going to drop them. It's not totally kosher. Why? Because the leading term, if epsilon is finite, is small but finite, and n is very large, then these terms are already singular in this limit. So if I multiply something which is very, very singular by something which is suppressed, I still get something which is singular. So strictly speaking, I don't know if, perhaps I should resum these terms carefully by themselves and see what happens, but I'm not going to do this. I'm just going to drop this as a And actually, dropping these terms, it's kind of an original scene, which perhaps explains why supersymmetry in the end is not always there. But let's drop them. And if you drop them, what do you get? You're left with all these leading terms. And the leading terms, they correspond to diagrams in the perturbative expansion, which before I did average over H, they did not have any loops. So you see, this diagram here, it did not have any loops, and it gave me a leading term after I averaged over H. This diagram, it had a loop, even before the average. And as we discussed, this diagram was not singular close to 6D. It was only singular below 4D. So that was a subleading term. So after I drop these subleading terms, I'm left only with 3 diagrams. So the leading diagrams are the 3 diagrams. So I'm left with diagrams like phi h is equal to the single cross, triple cross, plus 5 crosses, and so on. Well, let me write it also. and I don't have to bother about any other diagrams. So this is a very important step. So if there are any questions, then you should ask. But since there are no questions, so let me call, well, this is not exactly equal. This is approximately equal, and I'm going to call this phi h of x, which is the sum of these three-level diagrams. And now I'm going to use a very basic fact that so this solving this sum of three diagrams, it's a classic approximation in quantum field theory, so it is equivalent to solving a classical partial differential equation. So phi h of x is nothing but perturbative solution to classical partial differential equation, which is the equation of motion of our action there. So it is the equation minus box phi plus v prime of phi plus h is equal to 0. That's a classic fact of quantum field theory. So if you drop loop diagrams, you are reduced to, instead of doing quantum field theory, you're just doing classical PDE. So now, from this point on, we can use this conclusion to derive the existence of supersymmetry. Unless there are any questions. I'm sorry?
But there are more diagrams, right?
Yeah, it is an infinite number of tree diagrams.
Yeah.
Sorry. Yeah. Sorry.
Sorry, can I ask? It's not the fact that you have the other diagrams that diverge below equal to 6 that are responsible for the breaking of SUSY. There's nothing.
If we are staying very close to 6, just below 6, there are no other diagrams. All the diagrams which diverge, they are obtained from these trees. But this is for epsilon infinitesimal. Now, if epsilon is small but finite, this argument is not very rigorous. So, in fact, it's kind of dangerous to argue diagram by diagram. It would be nice to have some renormalization group understanding of what's going on, and that we will discuss next time. But this also has some value to it. So let's pursue. Any other questions? So now we are going to use this to compute the correlation functions, because you see, suppose that you want to compute something like phi h average, or in our approximation is going to be the same, phi h average. We just said that we are to compute these averages. We just said that we are allowed to replace phi by phi h, which is just a classical sum of these diagrams. So let's do this. So this is nothing. We just said that this is nothing but integral over h phi h of x, phi h of y. I'm just considering some example. This is x and y. And I'm supposed to average over h. So h is so I'm averaging over h with the Gaussian weight. So I reduced the problem of computing correlation functions where I was first supposed to average over phi and then average over h. Now in this formulation, I no longer have to average over phi. I just supposed to take h, solve this classical PDE, and then average over h at the end. So much simpler problem. And the claim, the claim of Parisi and Sourlas that this is supposed to give the same answer at long distances as just doing the complicated path integral of phi, h, and so on. Miraculous, no? So let us proceed with this logic. I don't have here any path integral over phi, and now I'm going to put back a path integral, but a very simple one. So I'm going to write this as integral over h, integral over phi. So here I have phi of x, phi of y, but I don't want to integrate over all phi's. I want to restrict myself only to phi's which solve that differential equation. So I'm going to put here a delta function, which says that it's a functional delta function. It's a delta function in the space of phi's, which says that minus box phi plus v prime of phi plus h has to be equal to 0. And also I have this e to the minus integral h squared over 2 delta ddx. Is this correct? Does this sound reasonable?
It's the identity.
Well, actually made a mistake here. It's not an identity, because if I just wrote it like this, then would be wrong, because then let us retrace the logic. If I just had this expression, then what I could do, I could find the solution of this equation. Then I would get this expression here, but then around the classical solution, there would be fluctuations, and I would be supposed to include a determinant describing fluctuations around this classical solution. But here there is no determinant. There is no determinant. It's just I'm supposed to really take this phi h, and there is a factor 1. There is no determinant here. So I have to get rid of this determinant. So it means that I have to insert here a factor. Determinant, it's a functional determinant of the operator minus box plus v double prime of phi. So it's an operator which describes fluctuations around this solution. It's the determinant, and I have to multiply by the determinant. Now it's an identity. Okay, let me do now another formal manipulation. I am going to exchange the order of integration. I'm going to integrate over h. So then I'm left with integral d phi, phi phi, which is just insertions. And then I have e to the minus integral. Integration over h is trivial, so just the delta function. I'm going to do the integral over h doing the delta function. So I'm going to get here minus box phi plus v prime of phi squared over 2 delta times the determinant. So I'm getting something interesting here. So I'm saying now my equations are telling me, okay, these are just insertions, forget about them, but my equations are telling me that I'm supposed now to study a field theory with some weird action which is an action of fourth derivative in phi, because you see there's like box squared phi. If you ignore this interaction term, it's like box phi squared. So it's an action with fourth derivative in phi, but it's a positive definite action, like it's totally healthy action. And there is this determinant. Well, the determinant is annoying, so now I'm going to do another trick. I'm going to introduce here. I'm going to use the identity that a determinant, if I have a matrix A, well, it's like an n by n matrix J, then the determinant of the matrix, I can reduce it. I can represent it as a Grassmann integral over d psi bar d psi e to the psi bar I a psi. So what I'm doing here is I'm introducing Grassmann variables psi bar 1, psi bar n, and psi 1, psi n, and I'm integrating over all of them. So there is this identity. So now in the functional context, this identity becomes that the determinant of this operator minus box plus v double prime of phi is equal to the integral, functional integral over fields psi bar and psi times e to the integral psi bar of, well, it's a field. Now psi bar becomes a field, psi a field. So there is an operator here, psi, and integral over d dx. So, well, why did I do this trick? Well, because in field theory, the determinant is a non-local object. It's hard to work with it. But now I'm representing my determinant by some term in the action, which involves local fields, psi bar and psi, which are Grassmann fields. So this is a little bit weird in the sense that my Grassmann fields are fermionic, but they do not carry any spinor indices. They are Grassmann fields, but they are scalars under rotation. So usually in quantum field theory, in particle physics, when you have fermionic fields, then by the spin statistics theorem, they always come in spinor representations of the rotation group. So this is, in particle physics, this is forced on us by unitarity of our theory. But here we're doing statistical mechanics. Unitarity is not a rule of the game. In fact,
I mean, ghosts always go the wrong way, don't they?
I'm sorry?
Ghosts always go the wrong way if you're doing Padea-Popov.
Ghosts, yeah. So ghosts are an example of this phenomenon in also in particle physics. There, you have to then go to some through some arguments to show them why this doesn't violate unitarity. In fact, there's some constellation between ghosts and other unitarity violating effects. So here, violation of unitarity is real. So the theory we are studying is non-unitary because it's statistical physics, because it's a disordered model, and we will see in the next lecture that you can recover the same model from replica formalism in the limit when the number of replicas goes to 0, and when something goes to 0, clearly this is not unitary. So we shouldn't be so scandalized by the fact that we are encountering this spinless scalar fields, spinless fermionic fields. So,
But it's not a feature of your ignoring the loops.
I'm sorry?
So it's not associated with your ignoring the loops, with your...
It's, it is. So so now I'm going to show you an example that if I didn't include these fermionic fields, then the perturbative expansion obtained from this action, it would not agree with what I'm supposed to have here without loops. On the other hand, if I do have the fermionic fields, then the loops of fermions are going to cancel some other loops appearing, and in the end you're going to end up with something which is equivalent to not having any loops. So the last trick that I'm going to do is, I want to also reproduce this. So I don't like this term, which is a square of a term with second derivatives. So I'm going to also introduce another auxiliary field, which I'm going to call omega. And so the action that I'm going to consider, the final action, is this. It's minus delta over 2 omega squared plus omega times minus box phi plus v prime of phi plus the term with fermions, psi bar minus box plus v double prime of phi psi. So this is the Parisi-Sourlas action. So if I integrate over psi bar and psi, I get the determinant. If I integrate over omega, omega is just an auxiliary field. If I integrate over omega, I am getting this term here in the exponential. So this is just an equivalent form of the action. Well, it's integral of everything over t dx.
Just one question. But if you integrate of omega, you get plus in the exponential.
Well, no, because you see, omega here is with the wrong sign. So omega has to be either integrated along imaginary axis, or in fact, it's better not to think that it's better not to think that omega has to be integrated over, because it enters in this very simple quadratic way in the Lagrangian. It's just best to think that omega is an auxiliary field, which is always fixed to this so to the value to the box phi plus v prime of phi. So if you don't like omega, one may not introduce it at all. You can just kind of keep working with this form of the Lagrangian. Okay, you always have to introduce psi's, but really it's not a problem to introduce omega. And the fact that omega has a wrong sign in the action, it's not a problem, because really omega is just an auxiliary field. And so now the claim is that perturbative expansion coming from this Parisi-Sourlas action, this is the first claim, is exactly equivalent to perturbative expansion coming from this, keeping just the three diagrams and then averaging over h. So here there is no longer any h. I just have these fields phi, omega, and psi. I just have to write diagrams Feynman diagrams in terms of these fields. And this is supposed to give me the exact answer, the same answer. Let me give you one example how this happens. Yeah.
The two-point function you didn't explain, right? The connected. You explained the average of one-point functions, but you didn't explain how to get the.
where did I not explain?
At the top left, you explained that phi expectation value with h, phi of x of h, phi y of h, average. But you didn't explain what's below.
I didn't explain, but it's supposed to be given by exactly the same expression. Because you see, at long distances, as I showed here, at long distances, phi h and has exactly the same asymptotic behavior as this product of the one-point functions averaged.
Can you show like diagram by diagram? Yes, probably.
Yeah.
So this action gives the divergent, like what's going to diverge, right? So that's
It gives what in perturbation theory diverges, and so we would like to conjecture that if you now, instead of just doing perturbation theory, you do renormalization group on this section, then you're going to find some renormalization group fixed point, and that renormalization group fixed point is the correct theory for the critical behavior of the model.
And then can I understand this just now what you said as if I see the difference, then it would just be this, the phi square, the m square, like the mass term, which doesn't diverge. So that's why it's these two are the same. Like the difference between these two is just what you would get by this m square type. At tree level, you would just get this whatever, just the usual 2-point function in the massive field, right? So that's just.
I'm not sure I understand what you have in mind.
Like if I try to compute both of these things at tree level, then the only difference.
Well, I'll give you. I'll write you some my way of understanding this equivalence in a second. But let me first show you. Let me first convince you that really perturbation theory agrees, and that fermions are important. So from this action that I wrote there, you can derive. From the quadratic part of the action, you derive the propagators. So it's very easy. I leave it as an exercise. So there is a propagator phi omega. In momentum space, it's 1 over k squared. Then there is phi. It's delta over k to the fourth. Interestingly, also, okay, psi bar psi is also 1 over k squared. And then finally, omega omega is equal to 0. You see, even though there is omega squared term in the action, but to compute the propagators, you have to write the kinetic term and you have to invert the matrix. The matrix is the matrix is off diagonal, and so because of this, you don't get any omega propagator. So from here we can recover scaling dimensions of the fields. From the scaling of the propagator, and these scaling dimensions are so the field phi, well, let me start with omega. Omega gets scaling dimension d over 2. Psi and psi bar get scaling dimension d over 2 minus 1. And phi gets the smallest scaling dimension d over 2 minus 2. And notice that the scaling dimension of phi is equal. We can write it as d minus 2 over 2 minus 1. And the reason why it's interesting to write it like this is that this expression is the scaling dimension of the free scalar field, free scalar in d minus 2 dimensions. So recall that in the end we are going to show that this theory shows dimensional reduction. So there's going to be a correspondence between this theory in d dimensions and another theory in d minus 2 dimensions. And this equality of dimensions that we see is the first sign that something like that may happen. And you can write down also the couplings. So as I said, the potential is m squared phi squared plus lambda phi to the fourth. Let me set m squared, let me put m equal to 0. Then the couplings that you see there are omega v prime phi gives me the coupling for lambda omega phi cube. And there's also a coupling psi bar v double prime psi. So this gives me the coupling 12 psi bar psi phi squared. So these are both quartic couplings with some interesting structure in the field space. But what you can now see is that you can now compute the dimensions of this coupling. So these are the scaling dimensions of the fields. So let us compute the scaling dimension of the couplings. So for example, this omega phi cube. So this has scaling dimension delta over 2 plus delta over 2 minus 2 times 3. So let us see. So this is equal to 2d minus 6. This is the scaling dimension of this coupling. And so this becomes, we would like to see where this is smaller than d. Because when this is smaller than d, then the coupling becomes relevant and we can hope for some non-trivial critical behavior. So this becomes smaller than d exactly when d is less than 6. And so by this argument, we recover that this model has upper critical dimension d equals 6. Okay, so this is all very suggestive. Just one last remark is that to see that how can we convince yourself that perturbation theory in this model, which I derived by doing these formal manipulations with path integral, let us just do a sanity check that perturbation theory has a chance to agree with what we had here based on 3-level diagrams. And so for this, I would like to compute the corrections to the 2-point function. So I would like to compute diagrams for phi phi. So on the 3-level side, the diagram that the interesting diagram that I'm going to have, which is the correction diagram, is going to come from here. So on the 3-level side, I'm going to have a diagram which is like this. So on the 3-diagram side, I have this diagram with 3 crosses and another one with 3 crosses. And now I connect these crosses by the propagators for the H field. So this is basically the only diagram of order lambda squared that I get on the 3-diagram side. Now, if I look for the diagrams on the side of this theory, then at first sight it looks like I have too many diagrams. So let us see. Let me denote this vertex by, I'm going to introduce some notation where this vertex is going to be denoted like this, while this vertex is going to be denoted by like this, where these are the psi and psi bar fields, and this is the omega field. And it looks, so let me first draw a diagram which reproduces this diagram on the tree side. So there is this propagator which migrates omega to phi. So phi, and this is, I have this propagator phi omega. This is 1 over k squared propagator. Then I have a vertex here which connects omega to 3 phi's. Then, okay. And then I do it in the opposite order. So I have here, I migrated to omega. This is 1 over k squared, 1 over k squared. And here I have propagators phi, which are delta over k to the 4th. So this diagram is exactly this diagram in my notation. But then there are two more diagrams actually that I can write, and they do not have any counterpart on this side. So these diagrams are like this. I can have directly 3 phi's and omega vertex, and then I can have here again 3 phi's and omega vertex, and then I can just connect them. This is a phi omega propagator, this is a phi propagator, and this is a phi omega propagator. This is a diagram which exists in this theory. And I can also draw another diagram using this vertex. So I have phi, and here I have psi bar psi. And now the claim is that these two diagrams cancel exactly. You can see that they have the same behavior. So there are two propagators 1 over k squared, and here also there are two propagators 1 over k squared. One propagator is just delta over k to the 4th. This is delta over k to the 4th. The loop diagram for fermions comes with a minus sign as usual. You can check the symmetry factors. You will discover that these two diagrams cancel exactly. So this is the only diagram which remains, and it reproduces you the tree diagram here. So that's non-trivial.
So the relevant diagrams here have order lambda square and delta cube.
Lambda squared, it's lambda squared delta cube, yes.
So here I think I can misunderstood. So I thought the relevant diagrams had the same order of lambda and delta.
It's a relative correction factor, because here the leading diagram already has a factor delta. Because the leading diagram for this correlator phi, it was already delta over, yeah. So it's delta times lambda delta, yeah. Okay, so the next discussion is going to be, I would like to discuss why this section has supersymmetry and why it has dimensional reduction. But I think it would be good to make a 10-minute break and then restart after the break. Okay, so let's resume. The next step is to show that this Parisi-Sourlas action has a supersymmetry. So there are several ways to see this supersymmetry, but the simplest way is to package these fields. So I have four fields, phi, omega, psi, and psi bar. So what I wish to do is I want to introduce y. Y is going to be a combination of x and two Grassmann coordinates, theta and theta bar. And I'm going to package everything in something which is called a superfield, big phi. So it depends on x, theta, and theta bar. And it's just a linear combination. So it's phi of x plus theta bar psi of x plus theta psi bar of x and plus theta theta bar omega of x. And I'm going to assign to theta and theta bar the same scaling dimension as x, so scaling dimension -1. And if I do this, then all terms in this equation, they have exactly the same scaling dimension. Okay, so after I've done this, so I have this y, and I would like to study supersymmetry transformations which act on y. So which supersymmetry transformations? So I'm going to introduce a metric on the superspace. So I'm going to define the length of y squared to be equal x squared minus alpha theta theta bar, and this parameter alpha is going to be kept fixed. I'm going to fix it later on in a second. And so this is going to be my metric, and I'm going to consider all transformations of superspace variables which are preserving this metric. So which transformations? So I'm going to consider super translations. So super translations, there's a normal translations, x going to x plus a, and also translations which correspond to theta going to theta plus epsilon, theta bar going to theta bar plus epsilon bar. So all these things, they preserve clearly the metric on my superspace. But I'm also going to consider super rotations, so that's very important. So super rotations are some transformations which transform my vector or supervector ya. They multiply it by some supermatrix RAB YB in such a way that the length is preserved. So y prime squared is equal to y squared. And just like ordinary rotations form a group, rotations which preserve the normal Euclidean length of a vector form a group. Similarly, these super rotations, they form a supergroup. And this supergroup has a name. It's called orthosymplectic group with d bosonic directions and 2 fermionic directions. So these are going to be my transformations. So let me give you an example of this super rotation. So for example, this is a super rotation example. So if I take delta x mu equals alpha epsilon mu theta, and delta theta bar is equal minus epsilon mu x mu, then you can check that that y squared is invariant to first order in epsilon.
Delta theta equals 0.
I'm sorry?
Delta theta equals 0.
Delta theta equals 0. Delta theta. So this is my this is my symmetry group. This symmetry group of the superspace is going to become a symmetry group of my quantum field theory that I'm going to build out of this superfield phi. And how it's going to become? Well, just like in usual field theory, when I have Lorentz invariance, and Lorentz transformations, they act on points in space, and I now make fields which depend on points in space to become a representation of the Lorentz group. So in the same way, I'm going to do it here. So I have my superfield which depend on y, and I'm going now to transform it. So my new superfield is going to be depend on phi of y plus dy. And this is going to be my phi prime of y. So this is going to be my transformation. And so let me just give you an example. So if I take transformation theta going into theta plus epsilon, so I have here phi. So let me do this transformation. So if I shift theta by epsilon, so I get here, so instead of theta, I give here theta plus epsilon, and here also I have theta plus epsilon, times theta bar omega. So this is the transformed field. Now I have to take this transformed field and I have to expand it again in theta and theta bar. And I have to read off the coefficients. So what do I see here? I here see, for example, epsilon psi bar, which is not multiplied by anything. So it means that this is going to be delta phi. So delta phi is equal to epsilon psi bar. And here I see epsilon theta bar omega. And so this is going to give me a contribution to psi. So delta psi is equal to epsilon omega. Actually, I'm sorry, it was epsilon theta bar, but I have to commute. Sorry, I made a mistake here because epsilon anti-commutes with theta bar, so there's a minus sign. Delta phi is minus epsilon omega. So you can work out similar transformations for super rotations, like here. Yeah, it's very important that here delta psi bar and delta omega are equal to 0. So similarly, you can, for super rotations, we can also work out these transformations. I'm not going to do this, but I'm going to note just one very important point, which is going to play a role in a second. This is an exercise, so work out these superrotation transformations, and notice you're going to get some expressions for delta phi, delta psi bar, delta omega. The only important point for what follows is that delta omega is going to be equal to epsilon mu d mu psi. What is going to be important in a second is that this is a total derivative. It's a total x derivative. And so now we have the following claim. I am going to consider the following expression. Integral d dx d theta bar d theta of some quantity that I'm going to call L. And L is equal minus 1/2 big phi minus box squared, well, let me say, minus already put here, box squared plus delta, no, minus delta, let me put minus delta, d theta bar phi plus v of phi. So why did I consider this expression? Well, two claims. The first claim is that this expression, if you take this expression, you plug it, you do the integral over theta bar theta. The claim is that this is equal, exactly equal, to the integral d dx of the action Parisi-Sourlas. That's the first claim. Now, this is an exercise, but let me show you just one term, how one term comes about. This is the easy term, namely the term omega squared over 2. So this is the easy one. So you take big phi, you apply d theta bar. So when you apply d theta bar, you pick up the term omega in phi. It's the term on top, because that's the only term which contains d theta and d theta bar. All other terms are going to vanish. So with the coefficient delta, that's a good coefficient. Now you have big phi also here. So big phi contains in it many terms, phi, psi bar. But we have to do this integral d theta bar. So the integral in Grassmann coordinates is the same as to do the differentiation in Grassmann coordinates. So it's going to again pick me up omega, and everything else is going to vanish. So this already tells you that I'm correctly picking up the term minus delta over 2 omega squared. Now the claim is that if you just do exactly the same exercise for all the other terms, you will reproduce precisely the Parisi-Sourlas section. So that's the first term, the first claim. It's the same v. It's the same v that we had here.
But phi depends on theta and theta bar, so it's just.
So we use the usual rules of algebra with Grassmann variables. It means that if you have v which depends on a function with Grassmann variables, you're supposed to expand out. You expand to first order. You expand to second order. You don't need to expand to more than second order because we have only theta and theta bar, and theta squared is equal to 0, theta bar is equal to 0. So you only have to expand to second order. And you see that in the action, in the Parisi-Sourlas section, we indeed only have second order derivatives of v. So that's how you're going to recover all those terms. Yeah. And so you expand to second order, and you always have to pick out the term proportional to theta bar, because we have here an integral in theta bar, and that's the only term that is going to matter. All the other terms don't matter. So it's the usual magic of superspace.
Is it possible to have here the central charges in the algebra of supersymmetry?
It's a very simple algebra. I'm not sure there are interesting central extensions. No, I don't know. Haven't heard about it. So that's the first observation. The second observation is that this action is going to be transform covariantly under supersymmetry. Under supersymmetry, what kind of supersymmetry? So I have here this operator in the square brackets. So this operator is a super Laplacian adapted to what superspace? So recall that I put their parameter alpha, which I kept free. So here I have delta, but the super Laplacian involves the inverse metric of the space. So it means that I have to fix, if I fix alpha equals 4 to the delta, then this operator is the correct super Laplacian. It's an easy exercise to see. And so the super Laplacian is an operator which transforms covariantly under my supersymmetry transformations. So what does this mean? It means that I started with phi, and I assume that phi transforms under supersymmetry transformations covariantly, which means like by shifting y, like there. The super Laplacian transforms also covariantly. So it means that L is an object build of phi's. A priori, I don't know how L transforms because there is this derivatives. But since the super Laplacian transforms covariantly, it means that L is also going to transform covariantly. So L is going to transform to L of y plus delta y, just like there, under supersymmetry transformations. And so if I now do a supersymmetry transformation, L is going to transform like this. In the integral, there is integration with respect to theta and theta bar. So I would like to show that the action remains invariant under supersymmetry transformation. So L itself does not remain invariant. L transforms. but I want to show that the integral of L remains invariant. Well, as I discussed here, under supersymmetry transformations, omega, which is the component multiplying theta, theta bar, it either doesn't transform at all, or it transforms as a total derivative. So this means that since I have here in L integrated with respect to theta and theta bar, which picks out its omega component, and there is an integral over x, since the transformation of omega is a total derivative, the action remains invariant. So that's the proof that the action is supersymmetry invariant. And so, yeah.
Is this parameter alpha like important, or could you maybe like rescale it away, or?
So now that I know that there is supersymmetry, I can realize that I can rescale it away by rescaling theta and theta bar. So you see, this parameter delta multiplies d theta bar. Let me rescale theta bar. I can set delta to whatever. So now that we know that there is supersymmetry, we can rescale it away.
Why couldn't you do it before? What do you?
Well, because you see, in order to do it before, I could do it, of course, from this action. But it would be a little bit miraculous, because if I rescale in this action, I would need to rescale omega, simultaneously rescale phi, psi bar, and psi. And then I would have observed that all these couplings that I have, they have the property that if I do this rescaling, then the structure of the quartic coupling here and the quartic coupling there, they remain the same, because they involve two different coupling constants. But it will turn out that they will transform homogeneously. So from this perspective, it's going to look a little bit miraculous. Now we know why this is true. Why is this the case? And so, what are the consequences of this supersymmetry? So the first consequence is that if you consider a two-point function, let us consider a two-point function of this big phi of x1 theta 1 bar, and phi of x2 theta 2 bar. The theory is supersymmetry invariant. It means that this two-point function is going to be a function of supertranslational invariant distance. So it's going to be some function of x1 minus x2 squared minus, and so let me set here delta equal to 2, and so alpha is also equal to 2, minus 2 theta 1 minus theta 2 times theta 1 bar minus theta 2 bar. So this I know just from the supersymmetry transformations. But now, okay, this is a two-point function of a superfield. From the two-point function of the superfield, I can extract two-point functions of the fields phi and omega, because I have to just expand here in theta. I expand this in theta 1, theta 2, in theta 1 bar. I expand this, and I extract from here the two-point functions such as phi of x1, phi of x2, psi of x1, psi bar of x2, and also phi of x1, omega of x2. Well, and finally omega as well. And all of these correlation functions, they're going to be expressed in terms of a single function f. This is what is called supersymmetric word identity, and this shows the power of supersymmetry. In particular, you discover that the two-point function of omega is equal to 0. Because, why is this the case? Well, because here, in order to have a two-point function of omega, you have to have here a term theta 1 bar, and here you have a term theta 2 bar. But if you expand this expression, you find that, there is no such term. So we have a non-perturbative supersymmetric proof that omega omega is equal to 0. And finally, the last property that, I would like to show today is that the supersymmetry implies dimensional reduction. So hopefully I'll be done in 10 minutes, which are left. So this works like this. What is the dimensional reduction? I have this supersymmetric theory. It depends on variables x, theta, and theta bar. I can consider correlation functions for different values of x, theta, and theta bar. But now I would like to do something interesting. I would like to take my theory, and I would like to put all operators. I would like to measure a correlation function. So this is going to be a d minus 2-dimensional submanifold. And this is going to be a plane which is determined by the conditions x perpendicular is equal to 0. So they're going to be d minus 2 parallel directions, which I'm going to call x hat. And I'm going to set 2 perpendicular directions to 0. And I'm also going to set theta and theta bar to 0. So I'm going to consider such d minus 2-dimensional plane. And I'm going to set my fields into the plane. So the claim is that such a correlation function with all fields set to this plane is equal to the correlation function of fields. So correlation function of phi of x hat and x perpendicular set to 0. I'm writing here phi because by setting theta and theta bar to 0, I'm basically focusing on phi components of big phi superfield, is equal to the same correlation function, so of the field phi hat, which only depends on x hat, okay, with endpoints. So I'm going to study, it's true for any endpoint correlation function. And this field phi hat is governed by the action which is a d minus 2-dimensional action. So it's integral d minus 2 x hat. And here there is minus is 1/2 phi hat d phi hat squared plus v of phi hat. So it's the same potential, and there is here a constant c, which I'm going to determine in a second. It's going to come out from our analysis. But notice that this constant, it basically amounts to, I can always absorb this constant by rescaling the fields, so it's not a big deal. So so this is the property of dimensional reduction, and this property has, as a consequence, if it is true, it has the consequence, as a consequence, the fact that the critical exponents of the theory in d dimensions of our Parisi-Sourlas supersymmetric theory in d dimensions should be the same as the critical exponents of the theory in d minus 2 dimensions. Because we can to measure critical exponents, you can take a 2-point correlation function, and you can see how it scales at long distances. And now we are saying that this correlation function is going to scale at long distances in the same way as a correlation function in the d-2 dimensional theory. So this is what I mentioned last time. And so this property of dimensional reduction has many proofs. There are some proofs based on perturbation theory. So that's kind of maybe the simplest way to prove it. You take this supersymmetric theory. Since the theory is supersymmetric, we can reorganize its perturbative expansion in terms of the superpropagator. So we can do Feynman diagrams in terms of superpropagators. Or in this theory, we have perturbative expansion in terms of usual propagators in d-2 dimensions. Now, if you are smart, you can stare at this diagrams written in terms of superpropagators, and you can notice that if all the external points sit at the d-2 dimensional plane, then there is a certain cancellation in all the integrals between the two fermionic and the two bosonic directions. So all those integrals, they basically amount to creating an extra constant C in every order of perturbation theory. And so that is one way to prove dimensional reduction. There are other proofs. You can try to argue for dimensional reduction from the conformal field theory perspective. Many proofs. But today I would like to give the simplest proof, which, in my opinion, which is due to John Cardy, and which goes as follows. Well, let me write my action, the supersymmetry action, as in the following form. So it's going to be integral dy. Let me split big L into two parts. Let me call it L perpendicular plus L parallel plus L perpendicular. And L parallel is going to be the same thing, minus 1/2. And I'm going to include the derivatives, only derivatives parallel to this d-2 dimensional plane, minus 2 d theta bar phi. And I'm also going to include the potential into this parallel part of the action. And into the L perpendicular, I'm going to include the perpendicular part, minus 1/2 phi d perpendicular squared. No, I'm sorry, actually, this has to go in the perpendicular part. So this is my L parallel and L perpendicular. And now I'm going to modify my action in a way that it interpolates between what I have in the SUSY theory and what I want to get in the non-SUSY theory. So I write action, and now I'm going to introduce also this interpolating parameter lambda and an external field, let me call it J. It's equal to the integral dy lambda plus 1 minus lambda delta function of x perpendicular delta function of theta delta function of theta bar times L parallel plus L perpendicular and plus J times phi. So this is just an integral in ddx, no, integral in dy, yeah. There's no integrals already there. So I introduced this external field J, differentiating with respect to this external field J. I'm going to compute the correlation functions of phi. And since I'm only going to compute these correlation functions of phi in the plane, this j is only non-zero, restricted. So it's only non-zero for x perpendicular equals theta bar equals 0. So there is also delta function here in j. If you wish. So that's my action. And I would like to show that now I'm going to interpolate. So if lambda is equal to 1, I have my initial theory. If lambda is equal to 1, I have initial theory. If lambda is equal to 0, then I have this delta 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 factor. So this delta 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 factor focuses on L parallel part. So, and it gives me this action here. Well, it doesn't yet give me the action because I have to put here the constant c. Now, after I put this constant c, it gives me the action that I'm aiming for. The part L perpendicular completely decouples when lambda is equal to 1. It's going to, when lambda is equal to 0, it completely decouples. There's no coupling between the perpendicular parallel fields. So I would like to show that nothing depends on lambda. So let me consider z lambda j, which is the integral over d phi e to the minus s lambda j. I would like to show that d z lambda over d lambda is equal to 0. Well, if I show that, then I mean for any lambda, I'm going to show that this is equal to 0 for any lambda.
So the field J is coming from where?
It's an external field. So I keep it fixed. I'm going to show that the partition function as a function of j doesn't depend on lambda. So if lambda is equal to 1, then by differentiating with respect to j, I compute the correlation functions I'm going to in the original theory. If lambda is equal to 1, then by differentiating with the j, I compute the correlation functions in the non-supersymmetric theory. So if z doesn't depend on lambda, then I'm done. So j is going to be fixed, arbitrary, and lambda is going to vary. So how do I show that? Well, I just look at how the action depends on lambda. So the only term which varies with lambda, so if I differentiate the action with respect to lambda, I'm going to get what I'm going to get. I'm going to get 1 minus constant c delta x perpendicular delta theta bar. I'm going to get L parallel, so it's going to be 1 point function of L parallel, which depends on x parallel, x perpendicular, theta and theta bar. Right? In general, it depends on all of these things. It's computed at lambda and j non-zero. And now I have to integrate everything in dy. Right? So this is the computation that I have to do in order to compute the variation of z lambda. And I want to show that this integral is going to vanish. So how do I show this? Well, the second term is easy. So the second term here, I do this integral delta function theta bar. This just set here everything to 0, all these components. So let me look at the first term. So I want to compute, the non-trivial part is to compute this integral over dy to integrate this 1 point function. So how can I show, so basically what I want to show is that the integral of this 1 point function in x perpendicular theta and theta bar is the same as just setting these 3 variables to 0. So how can something like that happen? Well, what I'm going to use is the following. Look, I split the action into two parts, L parallel and L perpendicular. By doing this split, I definitely broke most of my supersymmetry of my action. But there is one part of the supersymmetry which survived. Namely, the rotation in the x perpendicular theta, theta bar directions are not broken. Because all terms in the action, they preserve this x perpendicular theta and theta bar. They all enter in the combinations which preserve the rotation around my plane. So it means that whatever this one-point function is, I don't know what it is, but it is some function. Okay, it's going to depend on x perpendicular, it's going to depend on lambda, on j, but it's only going to depend on these orthogonal directions in a combination x perpendicular squared minus 2 theta, theta bar. This just follows from symmetry. And so now there is the following thing. So if I take this function and if I integrate it over dx perpendicular d theta bar d theta, f, which only depends on x perpendicular squared minus 2 theta, theta bar. How do I do this integral? Well, as we discussed, I'm supposed to expand it in theta, theta bar. And I'm supposed to pick up a term proportional to theta and theta bar. So this is equal to integral d to x perpendicular minus 2 f prime of x perpendicular squared. And okay, this measure of integration is what? It's so it's dr, it's rdr, so it's 2 pi rdr, so it's pi r squared. So what do I get here? I get 2 pi integral f prime of u, where u is equal to r squared, du, minus 2 pi, from 0 to infinity. That's what I get. So it is 2 pi f of 0 minus f of infinity. Well, f of infinity vanishes. Why does it vanish? Because I have all sources j sitting at x perpendicular equal to 0, and infinity means that I'm going to x perpendicular going to infinity. So at large distances, there's going to be no correlation function, no correlation. So f at infinity is going to vanish. So I'm left with this f of 0. And f of 0 is precisely the term that I get from here, from integrating these 3 delta functions up to a constant c. So I have here a factor of 2 pi from integrating over angular variables. So what it means is that I'm supposed to fix here c is equal to 2 pi. So c is equal to 2 pi. Well, that's the end of proof. So this is Cardy, 1983. It's an interesting argument. And one little puzzle for me is that this is not, so in supersymmetric quantum field theory, there is a technique which is called supersymmetric localization, which sometimes reduces path integrals in supersymmetric quantum field theories to some loci consisting of specific fields, specific field configurations. So this argument is not a supersymmetric localization argument. It's written like this. It's a little bit different because well, it's not. So, for example, what would be a supersymmetric localization argument? it would be something like that. I am doing a path integral over all fields phi, and in the first step I would reduce it to a path integral over fields phi which are invariant under rotations. And then in the second step, I would show that the integrals over field phi which are invariant under rotations is actually equal to the d minus 2 dimensional path integral. But this Cardy argument is like goes straight to the point. It kind of cuts through. So actually I'm not sure, I don't know of a good argument which would follow more the supersymmetric localization philosophy. So it would be interesting to work it out. So that's basically all I wanted to say today, but you see now where we are. So we derived this supersymmetry using the Parisi-Sourlas original paper from '79. We showed the dimensional reduction. We know that the dimensional reduction doesn't always work, so something must go wrong somewhere here that I talked to you today. So what is wrong? Is it the dimensional reduction as a consequence of supersymmetry, which is wrong? Or is it the derivation of supersymmetry itself, which is wrong? So in our theory, and I think most of the people agree, the fact that the supersymmetry implies dimensional reduction, this is solid. So there are many arguments for that. There are perturbative arguments, non-perturbative arguments. So we take it as a solid piece of the puzzle. On the other hand, the derivation of supersymmetry from the random field Ising model is not as solid. The derivation that I gave today, it was based on this argument. Let's go through all diagrams and let's see what are the most important diagrams. So that's not a very safe thing to do. It would be nicer if we could reformulate this argument in the renormalization group language. And so that's what we are going to do next time on Wednesday. And we will see that while doing that, we will discover that there are some new effects that have to be analyzed. And it is in those new effects that there is, according to our theory, the resolution of the puzzle.